യൂട്യൂബിലും ലൈവ് ഓണാണ്.
ഓക്കെ പ്രസിഡന്റ്
തുടങ്ങാം.
തുടങ്ങാം. കറക്റ്റ് 8 മണി ഷാർപ്പ്.
Meeting is called to order. After silent prayer for 5 seconds, we will start the meeting. Thank you all.
ഗംഗ മേഡം ഒന്ന് അൺമ്യൂട്ട് ചെയ്തിട്ട് പറഞ്ഞോളൂ.
കേൾക്കാവോ ഇപ്പം?
കേൾക്കാം, പറഞ്ഞോളൂ മാഡം.
Respected National Incoming National President Giri, Secretary Binil, and all the members, our Secretary Sen, and all the members who are present here, welcoming everybody to this meeting. Today, Dr. Vijesh Venugopal, HOD of Department of Anesthesia, KMCT Medical College, Calicut, is going to present the topic fundamentals of mechanical ventilation.
Madam, you are not audible. Madam's connection poi.
Secretary.
Sir.
Hi, Nasser sir. Good evening.
Sensor unmute ചെയ്തിട്ട് പറഞ്ഞാലേ കേൾക്കുള്ളൂ. Sir, കേൾക്കുന്നില്ല നമ്മള്.
Yes, good evening. I have joined.
Sorry.
Sir, welcome to this meeting.
Okay, thank you.
Okay, now I think it is audible.
Now it's
Yes,
audible.
yes.
Please, sir.
Yes. So today's topic is a very interesting topic. It is the fundamentals of mechanical ventilation. The speaker is Dr. Vijesh Venugopal. I think it's no special introduction because he is not to all of the members of ISA Kerala. But for the formality, I wish to introduce him. Dr. E.R. is MBBS from Government Medical College, Thrissur, and MD in anesthesia from Baroda Medical College. At the PDCC in cardiac anesthesia at Amrita Institute of Medical Science, Kochi, and PG BEM from George Washington University, USA. Currently, he is working as a professor and actually the Department of Anesthesiology and the DNB coordinator of KMCT Medical College, Calicut. And above all, he was the scientific committee coordinator of ISA Kerala State Branch for 2 years I think 2 years back, I think so. And now he is currently the governing council member of ISA Kerala State Chapter. With these words, I introduce Dr. Vijesh Venugopal to all of you. Sir, thank you, and kindly have the presentation, sir.
Sir,
Dr. Vijesh Venugopal.
Sir, meanwhile, I got to say a small announcement. Shall I show the screen?
Yes.
So our next PG update will be held on next Saturday. The topic will be neuromuscular junction and neuromuscular blocking drugs by Dr. Usha Shennai, additional professor, Department of Anesthesiology, Jubilee Mission Medical College. And the second topic will be neuromuscular blocking drugs by Dr. Jerry Paul. He is the professor in anesthesia from Amrita Institute of Medical Sciences, Kochi. And our third topic will be a case discussion on cataract surgery. The examiners will be Dr. Radha K.R., professor, Department of Anesthesiology, Government Medical College, Calicut. And the second examiner external will be Dr. Anand Bengare, professor and HOD of Shema K.S. Hegde Medical College, Mangalore. So I request all the PG students to join our PG update on Saturdays at 6 p.m. and request all the teachers to help guide the PG students to join us. And thank you. Over to Vijesh sir, please.
Okay, thank you, Binil, and thank you, Sensor, for those kind words. I'll just share the screen. The screen is visible, I believe.
Yes, visible.
Yes, yes.
Yeah. So today we'll be dealing with fundamentals of mechanical ventilation, and the outline of the talk would be we'll just go through the history, and I think we should know something about the anatomy of the ventilator. Then we'll go to some of the basic principles, and then, as Sensor told me, basic modes of ventilation will be discussed today. Newer modes, probably I'm not going to the details. We'll do it at some other time. Followed by what I have learned about mechanical ventilation over the last few years, and something about extubation, thought for the day. And if possible, we will do a simulation of mechanical ventilation through a simulator. So that's what we are going to do over the next probably 40 minutes. And coming to the topic as such, it's mentioned in Genesis 2:7 that the Lord God breathed into the nostrils of man the breath of life, and the man became a living being. And that was probably the first recorded artificial respiration. And the origins of mechanical ventilation has been traced back in history to one of the greats of anatomy, one of the great anatomist, Galen, who suggested that positive pressure ventilation is going to be the life-saving procedure for people who don't breathe. However, the first published scientific paper on mechanical ventilation was by Andreas Vesalius, who said that after making an opening in the trunk of the trachea, you put in a hollow tube of reed or cane and then blow into this, thereby giving positive pressure ventilation. However, this did not pick up. And the main reason was in the early 19th century, this positive pressure ventilation was uncontrolled, and many of the patients or many of the people who were put on these type of ventilators, crude ventilators, developed pneumothorax and died. So this fell into disrepute, and then came the negative pressure ventilators, because this mimicked the physiology of human beings. And Drinker and Shaw's iron lung was the first device that achieved widespread use in the 19th to the mid 20th century. And this is what the iron lung looks like. This is where the patient lies, and his head will be out of this box, and the foot will be out of the other side. And then this box is closed and negative pressure is applied and the lung expands. But since this was very cumbersome, they devised a chest kyra, where it is applied over the thoracic cavity and negative pressure is applied and the chest will expand. So this is another technique, the chest kyra. However, the turning point in the history of mechanical ventilation came in 1952 with the Copenhagen polio epidemic. In the very first month of the polio epidemic, 31 patients developed respiratory paralysis and 27 patients died. That is a whopping mortality of around 87%. A very famous anesthesiologist in Denmark, Dr. John Ibsen, was asked to help. He suggested that instead of this form of negative pressure ventilation, we should do positive pressure ventilation. And 200 patients were tracheostomized, and a manual anesthesia bag with a to and fro system with carbon dioxide absorber was introduced. And this was manned by medical students and other hospital personnel. So this was the device that he used. He did a tracheostomy, put in a tube, and then ventilated those patients. Almost 200 patients were ventilated. And this is how the polio ward looked, where the iron ventilators were kept and people were being ventilated. So Dr. John Ibsen, he proposed the early application of positive pressure ventilation, and he's known as the father of intensive care medicine. And what did it do? From a whopping mortality of 87%, the mortality came down to 25%, and mechanical ventilation with positive pressure was shown to be an amazing tool. So we now see what is this ventilator. A ventilator or a mechanical ventilator is an automatic machine which is designed to provide all or part of the work the body must produce to move gas in and out of the lungs. The act of moving air in and out of the lungs is called breathing, and more formally it is referred to as ventilation, as shown in this figure on the right hand side. So what are the different types of ventilators that are available? We have constant flow generators. Constant flow generators are ventilators that produce constant inspiratory flow. A high pressure gradient is established between the ventilator and the patient, and there is a constant flow pattern. But it does not care about the lung characteristics. So it will deliver the set tidal volume irrespective of the condition of the lung. So this constant flow generator behaves like a dictator. Then we have a constant pressure generator type of ventilators. These are ventilators which produce variable inspiratory flow. The machine develops a constant pressure that is only slightly above the pressure in the patient's airways. And so the flow varies with resistance and compliance of the lung. The only issue is your tidal volume is not guaranteed. So this is something like a democratic procedure where the lungs are taken care of. So these are the two different types of ventilators that are available. However, we'll move into the anatomy of a ventilator. We'll just rapidly go through the anatomy of a ventilator. The parts of a ventilator are, there are three important things that should be there in an automated ventilator. A source of input energy to drive the device, a means of converting this input energy into output energy in the form of pressure and flow to regulate the size of breaths, and a means of monitoring the output performance of the device and condition of the patient. So in short, it can be said that there should be an input power device, there should be a power conversion and transmission system, a control system, and an output. That is usually by flow sensors. So if you cut open a ventilator, this is how it would look like. You would have lines, the pressurized oxygen and the pressurized air coming into a blender, which is the pneumatic unit. And from the blender, the desired FiO2 will go through the drive mechanism, which could be the turbine. And this is controlled by the control unit of the ventilator. And of course, when the gas goes out, it goes out through the sensors. And then it will give you a feedback mechanism, and the feedback mechanism is going back to the control unit. So this is how a basic ventilator works. This is the small picture of the blender. And you can have the power source could be electrically powered or pneumatically powered ventilator, but the current ICU ventilators use microprocessor control. So they are classified as, they are both electrically powered, pneumatically driven, and microprocessor controlled ventilators. Now the power source could be a compressed gas or electricity. The bellow ventilators use force of compressed gases, and electricity is used as a power source by either the piston or the turbine ventilators. However, all the ventilators use electricity for the sensors and the control mechanisms. Now, what is the drive mechanism? The drive mechanism is part of the breath delivery unit. They develop and control pressure gradient between the ventilator and the patient. So there are two elements. It has both pneumatic and electronic modules. So one type of drive mechanism are piston ventilators. Now these piston ventilators, they do not require driving gas. They are driven by compression from an electric motor to move a piston, as shown in this picture here. And the piston just pushes and it creates pressure which moves gas within the piston to the patient's lung. The other one is the turbine ventilators. The turbine ventilator is an electric motor which is used to drive a blower which creates inspiratory flow and pressure. So this is a picture of a turbine. This is similar to your hair dryer, where you on the hair dryer and you get air blowing out. So the advantage of a piston and a turbine ventilator is it does not require the presence of compressed gas. The other drive mechanism is using the bellows. So here it requires the presence of compressed gas or driving gas, which pushes the bellows which contains the patient gas. So the driving gas is usually oxygen or air, but preferably oxygen. Now coming to the control system and circuit, you have a pneumatic circuit as well as electrical components. If you look at the pneumatic circuit, there are two types. There is a circuit within the ventilator, it is called the internal circuit. And there is a circuit which is outside, that is the patient circuit, your tubings, ventilator tubings, which you connect to the patient. So the internal circuit could be single circuit design, where there is only an inhalational valve which opens and the piston pushes air through the to the patient, and this is the most commonly used. We even have double circuit designs where it contains a bellows, and the bellows are compressed. The external circuit is very familiar to all of us. This is what we use for connecting the ventilator to the patient. Control types, again, it could be, again, this is an electrical component. It is open loop control system where the operator sets a parameter and it is delivered by the ventilator. There is no assurance of volume or pressure. But most of the modern ventilators use closed loop control system where the flow or pressure are set and measured with feedback to drive the mechanism, altering the output to maintain desired set levels. So here a microprocessor is used. So when a specific tidal volume is set, the ventilator adds to the volume if there is a leak in the circuit. So the ventilator will adjust the volume or pressure. The control panel, which this is the known as the ventilator cockpit or the user interface. It contains all the controls that are available and it displays very important parameters like the graphics. There are different types of control panels. It could be touch screen or it could be using knobs. And then we come to the flow control valves. Most of the current ICU ventilators use the proportional solenoid valve. We have expiratory valves, which are at the outlet. This closes during inspiration to direct gas flow to the patient, and it opens during exhalation, allowing the patient to exhale gas into the atmosphere. So this is the one which applies PEEP. There are 3 different types of expiratory valves in our ventilators. It could be either spring-loaded valves. This is just like our APL valve. Then we have the diaphragm expiratory valve, as shown the picture here. The diaphragm occludes during inhalation, and during exhalation, depending on the PEEP required, it will open the expiratory line to the atmosphere. If there is 0 PEEP here, as shown in C, it will be collapsed and all the air will come out. Whereas the amount of PEEP that you give to this diaphragm expiratory valve, so there will be a restriction and PEEP will be developed. The other third one is the electromagnetic valves. Here, an amount of electric current is adjusted to regulate the amount of force applied to the expiratory flow. So higher the level of the current, more the force applied and more the PEEP level. And this is the one that is now commonly available in our ICU ventilators. The last one is the sensors, or the flow sensors, which will give you the feedback. So there are many different types. The common ones are the heated wire flow, the one shown on the left. Okay, there's a small mistake. The one in the center is the ultrasonic one, and the one on the right hand side is the differential pressure flow flow sensors. So what it does is it will measure the flow that is going and give you an output. So that is briefly regarding the anatomy of a ventilator. What will you see? What are the different parts of the ventilator? Now coming to who needs mechanical ventilation. A person or a patient who has inadequate ventilation, that is hypercapnic pulmonary failure. There are umpteen number of causes which can cause inadequate ventilation. I'm not going into the details. It could be because of failure of oxygenation. Again, hypoxic pulmonary failure. Again, there are a number of causes. And the third one is inability to maintain an airway. And the fourth one is inadequate respiratory drive, probably our postoperative patients. So these are the 4 major indications for mechanical ventilation. So now coming to the basic principles of mechanical ventilation, very important that we know these principles before we go into the modes of ventilation. So you can imagine a ventilator as a boy blowing air into a balloon. So if you look at this picture here down, you can imagine this is as a straw. It is connected to a balloon, and this straw is your airway, and this balloon is your lung. So it's important to know the equation of motion. What it says is the pressure that is required to deliver a breath comprises of 2 different pressures. That is the pressure that is required to overcome the elastance of the lung and the chest wall, and also the pressure that is required to make air flow through the airways. If you come to the left hand side of the equation, the pressure that is required to deliver a breath could be from both the patient as well as from the ventilator. That is the pressure developed by the respiratory muscles as well as the pressure given by the ventilator. And this can be on the right hand side, it is the pressure that is used the elastic pressure as well as the resistive pressure. So in patients who are totally ventilator bound or paralyzed, the muscle component will be 0. So P vent will be, the elastic component will be elastance into volume, and the resistive component will be resistance into flow. So this very equation is very important from the point of view for understanding the working of a ventilator. So these are the control variables. So how many control variables are there? We have, you can either, the ventilator can control the pressure, the volume, or the flow. So ventilator can control only one variable at a time. The independent variable is the control variable. So if the pressure, for example, is controlled, if you are controlling the pressure, both the flow and the volume will be the dependent variable. So what is a pressure controller? A ventilator which controls pressure, but volume and flow varies with change in compliance and resistance. Here, if you look at this, the pressure waveform will be square or constant during inspiration. Coming to volume and flow controllers, the volume controller, the volume ventilator will control the volume. So the volume will be constant. But since what is flow? Flow is volume by time. So here, since volume is constant, the flow also will be constant. But what happens here is the pressure will vary with the changes in the compliance as well as the resistance offered by the airway. Now coming to the third one, that is the flow controller. As like a volume controller, the flow and volume will be constant and pressure will be varying. You look at this picture or the graphics, the one on A, you can see that the pressure part, there is a plateau. So that means that is a pressure controller. On the second B, you can see that the flow, there is a plateau. So that means this B part is a flow controller. And on the third column, that is C, you can see that is a plateau on the volume graph as well as on the flow graph. So this is a volume controller. So these are the three different types of controllers that are available. Now coming to the breath types, there are two different breath types. You have spontaneous breath as well as mechanical breath. The spontaneous breath is the patient will trigger and cycle the breath. The patient effort may be supported by the ventilator. The mechanical breaths are of two types. They are either mandatory breaths or assisted breath. Mandatory breath means breath is initiated by the ventilator, and assisted breath is triggered by the patient but is delivered by the ventilator. I can show you a picture here. If you look at the bottom part, you can see a sinusoidal wave. So this is spontaneous ventilation, right? And if you look at the pressure tracing, I think you can see my arrow. You can see here that the patient assisted breath, there is a dip in the pressures. So this is a assisted breath. Whereas in the second one, the bold line, there is no dip in pressure. So this is a second breath is a machine controlled breath. So this is just, you can compare it like doing a pull-up. The control breath, the control breath, there is no work done by the patient. The ventilator does all the work. In assisted breath, the patient will start the work and ventilator takes over the work. And in supported breath, the patient is able to do some or most of the work and the ventilator only assists to finish the work. So just like giving a pressure support. Now, if you look at this pressure tracing, there are different components of the breath. If you look here, the first part, that is end of expiration to the beginning of inspiration. You can see there is something called a triggering part here. Then there is delivery of inspiration, followed by end of inspiration and beginning of exhalation. And the expiratory phase is the one that is showing the PEEP level there. So there are 4 different phases. So each phase will be the ventilator will use variables to initiate or limit each phase of ventilation. So these are called phase variables. So this can be remembered as 3 T's of ventilation along with PEEP. So the first 3 are T's and the last one is PEEP, or it is the baseline variable. The first T is the trigger, which will initiate a inspiration. So trigger variable could be either machine triggered or patient triggered. All machine triggered breaths are time triggered because it is determined by the rate that you're setting on the ventilator. Patient triggered ones could be triggered either by pressure or by flow. Volume is very rarely used. So most ventilators even will give you an option to give manual breath button. So patient triggering, the breath is triggered because of the effort that the patient puts. So there is an important factor there, the trigger sensitivity. Now coming to time triggering, the ventilator triggers breath at preset intervals. The time for mandatory breaths is based on your cycle time, that is the respiratory rate that you have set. So if you have set 12 breaths per minute, the cycle time is 1 minute is 60 seconds. So 60 divided by 12. So each cycle time is 5 seconds. So the machine will give one breath every 5 seconds. So that is time triggering. Pressure triggering. The ventilator breath is triggered by a decrease in the pressure below baseline. Usual sensitivity we set is minus 0.5 to 2 centimeters of water. Now coming to flow triggering, it is very important to know that there is something called a base or a bias flow present in the circuit immediately after exhalation. And this is usually up to around 5 to 8 liters per minute. And the flow trigger we set usually 1 to 5 liters, or commonly we set it 2 liters per minute. So when a patient decreases flow to a set level of flow trigger, an assisted breath is delivered. So that is flow triggering. If you look at this picture here, the flow B and flow A. Now here the patient is exhaling. If you can see my arrow, the patient is exhaling there. And at the end of exhalation, there is a base flow within the ventilator. And now this patient will take a breath. He will now inspire. So there will be a drop in the pressures or the drop in the flow that is coming in the B limb. And this is detected by the sensor, and this is detected as a flow trigger. And on the flow scalar, you can see there will be a small uplift. To make it more clear, I can show you in this picture. In a pressure trigger, there will be a drop in the pressures from the baseline. Whereas in flow trigger, actually, there is an increase in from the baseline, the flow loop just goes, rather the flow scalar just moves a little up. So that is the flow trigger. So the advantage of flow triggering is it is more comfortable for the patient, and you don't have to cause a big drop in pressure to get the breath. So this is flow trigger would be more comfortable for your patient. So this is just again telling something about the base flow, and this base or bias flow, which is happening immediately after the exhalation till the next inhalation, is the one which provides for flow triggering. Now, this very important component or trigger sensitivity is the amount of effort required by the patient to initiate a machine breath. So again, it's just a repetition. Pressure triggering, the sensitivity we usually set from 0.5 to 2 centimeters, and both of them are negative of water. And flow triggering, again, we usually set at a value of around 2 liters per minute. The other triggering methods are manual triggering, where you can just press a button on the ventilator and the operator will trigger a ventilator breath. The other newer one is the neural triggering, where this monitors the electrical activity of the diaphragm. This is used in neurally adjusted ventilatory assist, which is a newer mode of ventilation. So that is regarding the first T. First T is triggering. So triggering is a very important component of ventilation. The second T is the target, or something called as limit variable. The correct terminology is limit variable. We can remember it as the second T, that is targeting. What it does is it limits inspiration, but it does not terminate the phase. It could be pressure limited, volume limited, or flow limited. That is, it will limit the peak inspiratory pressure during inspiration. If it is volume limited, it will limit the amount of tidal volume delivered during inspiration. If it is flow limited, it will limit the amount of flow during inspiration. So these are the three different forms of limits that are available. Another very important thing that is affecting the inspiratory phase is the ramping or sloping. This is the ability to adjust how quickly flow is delivered during the set inspiratory time. This is referred to as the inspiratory rise time. So these are some additional points that we are adding into the principles. So if you look here, you can see that from the baseline, from the initiation of your inhalation till the limit is reached, this time is referred to as the rise time. So if you keep this rise time around, if you keep it as 1 second, there is a very slow rise of this one, and you can see that there is a, you can see in the picture below, there is a slow rise. And here you can see this is a moderate rise. And the third one is the fast rise, where you can see there is a beaking of the this one. So you will get the flow is reached, or the limit is reached very fast. So ideally we keep this to around 0.2 seconds. So around 200 milliseconds is the one, if the rise time is usually set. But in patients with air hunger, you might have to keep even a smaller, you need to give a very small rise time so that the patient's air hunger is satisfied. So that is regarding rise time. The third T is the termination phase, or it is called, in proper terminology, it is called cycling. So cycling is the variable which terminates the inspiratory phase. So it could be pressure cycled, volume cycled, flow cycled, or time cycled. So this is what it does is it will terminate your inspiration, whereas limit does not terminate inspiration, it will only limit the inspiration. So time cycling, it depends on the time that you set. If you keep your inspiratory time as 1 second, at the end of 1 second, the ventilator will go into expiration. So during this phase, you can add something called inspiratory pause. So this is at the, when during the cycling phase, there is at the end of the inspiration, you can give a inspiratory pause. This is an extension of the inspiratory time by exhalation valve remaining closed after a set tidal volume has been delivered. This is referred to as a inspiratory hold or an inspiratory ventilation, but very commonly it is used with volume control ventilation to calculate the effective static compliance. Whereas in pressure control, the inspiratory time is long enough for the pressure to equilibrate within the lungs. Okay, so here at the towards the limit, there is a application of hold. So what happens is, from the peak pressure, there is a plateau that is developed. Okay. So what is this peak and plateau pressures? Peak pressure is what is generated when air flows into the airways, and plateau pressure is when the flow stops. So this is now giving you the alveolar pressure or the lung compliance. So if you have an increased airway resistance, or the peak inspiratory pressure is high and the P plateau is normal, that means your airway resistance is high. While if you find that your P plateau is more and your PIP is remaining constant, it is more of a decreased compliance. So another important component, or rather value that is very important, that is coming up now, is the value of the driving pressure. Again, this is driving pressure you can obtain from this graphic. Driving pressure is the difference between plateau pressure and PEEP. And we should always try to keep this driving pressure less than 15, and your plateau pressure should be less than 28 centimeters of water. So what is this driving pressure? So driving pressure is nothing but, it is a ratio between the tidal volume generated and the static compliance. And the importance is if the driving pressure is increasing, if you look at this picture on the right side, you can see the mortality. There is a corresponding increase in the mortality. If the driving pressure decreases, the mortality to decrease. So always target a driving pressure of less than 15 centimeters of water. And this is more important during when you start ventilating ARDS patients. So this is a just a rubric showing the If you have a driving pressure that is less than 15 centimeters of water, you keep the same ventilatory parameters. But if you have a driving pressure which is more than 15 centimeters of water, that means you have a decreased static compliance for your lungs. So it could be ARDS or it could be some other restrictive lung disease. So you'll have to do recruitment maneuvers, prone the patient, and all other maneuvers that are needed. And it's still your driving pressure is more than 15. Then you'll have to consider decreasing your tidal volume to less than 6 ml per kilogram of ideal body weight or predicted body weight. So now coming to flow cycle, that is the inspiration ends when a preset flow is reached. The pressure support ventilation is the most common application of flow cycling. So when it was first developed, the breaths ended when the flow dropped to 25% of the initial flow. But now you can have a different varying percentages of expiratory flow from 5 to 80%. I can show you the small picture here. Here, the expiratory trigger sensitivity is at 10%. So that means towards the end of 10% of the initial flow, what happens is it triggers back to expiration. Here you can see at 25%, at the end of 25%, means only 25% of your flow is remaining. So at that time, it will trigger into expiration. So that is flow triggering. Here again, 50 at the end of 50%, it is triggering. So this is flow triggering. So what is this difference between cycling and limiting or targeting? So once the limited parameter is reached, flow is adjusted to maintain it. That means flow is continuing at limit. So this is the major difference between cycling and limiting. Most of us had most of us would have a confusion whether what is the cycling and limiting difference. This is the difference. Once the flow or once the limited parameter is reached, flow is adjusted to maintain it and flow continues. Whereas at cycling, there is end of flow. The flow stops and there is change from inspiration to expiration. Now that is regarding the 3 T's, and now coming to the baseline variable, that is expiration. So in expiration, you can modify it by, that is the baseline variable. You can either give a positive end expiratory pressure or a negative end expiratory pressure or a zero end expiratory pressure, which equals the subatmospheric pressure. So this negative one is used in your high frequency oscillatory ventilation, and most of us use the positive end expiratory pressure. So the applications of PREP are to increase your FRC, to increase your mean airway pressure, to improve your lung recruitment and improve the oxygenation. So now coming to the basic modes of ventilation, it is said that you should know this pyramid, that you should memorize the key terminologies. You should understand the 10 maxims of mechanical ventilation. You should classify the modes, compare the modes, and use the modes. This is according to Chatburn. So what is a mode? So mode is actually the control variable plus the breath sequence plus the targeting scheme. All of this together will give you what a mode is. So now coming to pressure ventilation versus volume ventilation. So pressure cycle modes will deliver a fixed pressure at variable volume, and volume cycle modes will deliver a fixed volume at variable pressures. So whatever is the control mode, the other parts would be the non-dependent variables. So there will be change in the other ones. So if you look at the pressure cycle modes, they are pressure support ventilation, pressure control ventilation, CPAP and BiPAP. The volume cycle modes are volume control, assist control, and the intermittent mandatory ventilation and SIMV. So coming to pressure control ventilation, here the ventilator will determine the inspiratory time. There is no patient participation. It's a control mode. So it is the ventilator which decides everything. So it is triggered by time. It is limited by pressure, and it affects only the inspiration. The disadvantage is it requires frequent adjustments to maintain adequate expiratory minute ventilation. So patients with non-compliant lungs may require alterations in inspiratory times to achieve adequate tidal volume. So here only the pressure is applied, and depending on the compliance, the tidal volume will change. So it is very important that we monitor the tidal volume for a patient who is on pressure control ventilation. So this is controlled mandatory ventilation. These are the graphics you can see here. There is a set pressure control level. You can set it from 0 to 20 or 30, depending on the tidal volume that is generated. So we can see that in the simulation. And the assist control is, again, it is patient triggered. You can see it, the trigger is here. You can see that these breaths are triggered, and this is time triggered. This is called assist control ventilation. Now coming to pressure support ventilation, here the patient determines the respiratory rate and the inspiratory time. It's a purely spontaneous mode. The parameters, they are triggered by patient's own breath. It is limited by pressure, and it affects inspiration only. It doesn't go into the expiratory phase. So the uses of pressure support are, it complements your volume cycle modes, and it can be used alone for if the patients, just before the patients are going to get extubated. So it's a weaning mode. And when CPAP plus pressure support is used, it is called BiPAP. So what is pressure support ventilation? Here you can see that this is the picture below. It is showing spontaneous ventilation. That is a sinusoidal pattern. Here pressure above PEEP is the setting variable. There are no mandatory breaths applicable on spontaneous breaths, and the flow cycling is there, which we have gone through the flow cycling, which terminates when the flow drops to a specified fraction of its maximum. And patient effort determines the size of the breath. You can see here in the bottom, you can see that when pressure support is applied, you can see that there is a increase in the pressures that are delivered. So it augments your spontaneous tidal volume, and it decreases the spontaneous rates and work of breathing. It is used in conjunction with spontaneous breaths, but very important to remember that there is no guarantee of tidal volume with changing respiratory mechanics. There is no backup of ventilation in the event of apnea. Coming to CPAP and BiPAP, again, CPAP is nothing but a constant PEEP, and BiPAP is CPAP with pressure support. So pressure support is applied only during the inspiratory phase. Now CPAP is PEEP set at around 5 to 10 centimeters of water, and BiPAP is CPAP with a pressure support. So pressure support you can set from 5 to 20 centimeters of water. And this is shown to reduce need for intubation and mortality in COPD patients. Now coming to the volume control modes, the control mode is the patient receives a set number of breaths and cannot breathe in between the ventilator breaths. It is similar to your pressure control, but here the volume is the one which is controlled. Or you set that the patient will receive 500 ml of tidal volume that the ventilator will deliver. Now coming to the assist mode, here the patient initiates all breaths, but the ventilator cycles in at initiation to give a preset tidal volume. So the patient controls the rate, but always receives a full machine breath. So here you can see this is a controlled mandatory volume targeted. You can see that this is volume targeted, and here you can see that there is a square wave pattern. So if you see a square wave pattern, you can say that it is on the flow. If you see a square wave pattern on the flow, you can safely say that this patient is undergoing volume controlled ventilation. So this is time triggered, flow limited, volume cycled ventilation. And if there is an assist, each and every assist will be supported by the ventilator. So this is assist control. So here, if the patient is taking breaths, like we are setting 12, if the patient is triggering the ventilator 20 times, all the 20 breaths will be given as 500 ml. So that is assist control ventilation. So this is the basic difference between a volume control breath and a pressure control breath. In case of a pressure control breath, you can see that there is a decelerating. You can see there's a decelerating flow pattern, whereas in case of a volume control breath, there is a square wave pattern. So if you see a square wave pattern, you can always safely say that the patient is undergoing volume control ventilation. However, recently we have different types of flow pattern even in volume control ventilation. You have the decelerating flow pattern, the square wave pattern, the sine wave, as well as the ascending or accelerating flow pattern. So now if you find a square wave, it is definitely volume control. But if you don't see a square wave, you cannot say that it is volume control, because these type of different flow patterns are also there in volume control ventilation. If you look at here, the minimum airway pressure is seen in decelerating flow. So that is an advantage if decelerating flow pattern is given for volume controlled ventilation. So if you look at these three different waveforms, flow waveforms, you can see that this square waveform, you can say, is typical of volume control, and the decelerating waveform is typical of pressure control. And in pressure support, you can see that there is a cycling that happens at either 25%, 50%, or at whatever we have set. There is a cycling or the end of flow, and there is cycling into expiration. So it doesn't touch the baseline. So this is the major difference on your flow time waveform. Square, it means it is volume control. If it is decelerating, touching the baseline, it is a pressure control. Whereas pressure support is the only mode where the cycling is, flow cycling is done by the patient, and the flow cycling is done here at 25%. So these are the three differences, or the difference you can see on the flow time waveform. Now coming to intermittent mandatory ventilation and synchronized intermittent mandatory ventilation. In intermittent mandatory, it is different from control ventilation. The patient can initiate own breaths in between the mandatory breaths. And it is different from assist, that spontaneous breaths are not fully supported by the machine with fixed tidal volume. There is no fixed tidal volume being given as in assist. So ventilator always delivers breath even if the patient is exhaling. So there can be breath stacking and other issues. So you can see there is a random chance of breath stacking and asynchrony, and this will lead to increased work of breathing, and there will be an uncomfortable feeling for the patient. So there are a lot of cons for this mode of ventilation because of the increased work of breathing and chance of barotrauma and volutrauma. So then came up the synchronized intermittent ventilation, where the breaths were synchronized to the triggering. So you can just see that there is something called a synchronization window. So this is the time interval just prior to the time triggering in which the ventilator is responsive to the patient's inspiratory effort. For example, you are setting a rate of 12. So every 5 minutes, in 5 seconds, that is, which is one cycle, if the patient triggers a breath, it will be supported by the ventilator. So if the breath falls during the synchronization window, then that breath will be supported. So ultimately, in synchronized intermittent mandatory ventilation, you will have three types of breathing. One is the patient-initiated assisted ventilation, shown in white, unassisted spontaneous breath, shown in blue, or rather grayish color, and the sinusoidal one, which is the unassisted spontaneous breath. So there are three different types of breathing in synchronized intermittent mandatory ventilation. However, remember that there is a great work of breathing during this mode. So it is always advised that you add pressure support to synchronized intermittent mandatory ventilation. So basic ventilatory modes you can summarize as it could be mandatory or spontaneous, and an overlap would be for synchronized intermittent mandatory ventilation and pressure support ventilation. So what do I use? Now there are so many possible modes. So there are two potential reasons. They are equally effective and some of them are equally ineffective. So to keep it simple, there are only two kinds. Either you have full mechanical ventilatory support or you give partial support. So as an initial step, the idea is to ensure adequate ventilation. So we recommend giving a full support, and subsequently you can go in for partial support, and once the patient is ready for extubation, you can put the patient upon pressure support ventilation. So now there are certain settings which you have to do to improve oxygenation. PEEP and FiO2 are adjusted. FiO2, if you adjust, you can just increase the FiO2 if your oxygenation is coming down. But you should remember, keep in mind the long-term toxicity when your FiO2 is kept more than 60%, especially the Paul Bunnell effect of convulsions and the Lorraine-Smith effect, that is the fibrosis of the lung. The other one that you can do is you can increase the PEEP. If you look at this picture here, you can see that there is edema between the alveolus and the blood vessel here. And if you apply PEEP, what happens? The fluid is displaced and there is more contact between the alveolus and the blood vessel. So it is you get more gas transfer. So what PEEP does is it increases the FRC, it recruits your collapsed alveoli, improves ventilation perfusion matching, and it enables maintenance of adequate PaO2. So the disadvantage is it increases your intrathoracic pressure, it can lead to ARDS and pneumothorax and pulmonary edema. Now, what are the ventilatory settings that you can use to improve ventilation? You can modify the respiratory rate, or you can increase the tidal volume, or the other methods to decrease PaCO2 or reduce muscular activity, and by giving neuromuscular blockade, you can minimize your exogenous carbohydrate load, and you can control any hypermetabolic states that the patient has. So these are the various techniques to reduce the PaCO2. We studied what are the techniques to increase the PaO2, that is increasing PEEP and increasing the FiO2. And now to decrease the or to improve ventilation, you can increase the respiratory rate or the tidal volume, and you can also reduce the use the other methods. So now coming to the newer modes, are we mad or are we making a difference by using these newer modes? Now we are not going into the details of the newer modes. Only thing is inverse ratio ventilation. Again, there is no statistical advantage. Prone ventilation, it is logistically very difficult. However, mortality, initially all the trials showed only improvement in oxygenation. There was no mortality benefit. But however, the Perceiver trial in 2013 by Guerin and colleagues demonstrated mortality benefit for proning patients. And especially now with COVID, definitely proning is shown to benefit patients. Again, HFOV, again, the OSCAR and the OSCILLATE trials which were done showed unclear mortality benefits. So coming to the standard ventilator settings, you can remember it as Murite. You have to set the mode, you have to set the FiO2, that is oxygen, you have to set the respiratory rate, you have to set the inspiratory, what is the inspiratory action that you have to do, and you have to set the inspiratory time and the expiratory action. So it's very important to know that you don't ventilate patients based on their body weight. You have to predict, you should get the predicted body weight or the ideal body weight. So it is unfair to ventilate patients. Suppose the patient is 100 kg, you cannot ventilate him based on 100 kg because as the patient becomes more or less obese, their lungs will be of the same size. So it mainly depends upon the height and the gender of the patient. So this is the formula which we all should remember. The predicted body weight is 50 plus 2.3 into height in inches minus 60 for males. And the same formula becomes 45.5 plus 2.3 into height in inches minus 60 for females. And most of the newer ventilators, if you enter the sex and weight of the height of the patient, you will get the predicted body weight. So you can set the mode, you can set the FiO2, the respiratory rate, you can set the tidal volume based on the predicted body weight, set the inspiratory time and the expiratory action, that is you can set a PEEP. So, but you should always be aware that the peak inspiratory pressure should be always less. The plateau pressure should be set to less than 28 and the driving pressure should be less than 15 centimeters of water. So Chatburn's maxims for understanding ventilator operation, there are 10 maxims and these are available in standard textbooks. You can just have a look. But very important that we monitor our patients. You should monitor the sensitivity that you have kept. You should monitor the tidal volume in case the patient is on pressure control ventilation. You should monitor the pressures, the airway pressures, especially the peak inspiratory pressure, plateau pressure, and the other pressures if the patient is on volume control ventilation. And along with it, you have to examine the chest of the patient, always auscultate. The very important to measure the cuff pressure is very important. Similarly, monitoring the arterial blood gas is also important along with the vital signs of the patient. And it's similarly, we get alarms, different levels of alarms, level 1, level 2, level 3 alarms are there. So very important that you just don't go on silencing the alarm, but see what the alarm is and manage. So 2 slides on general troubleshooting. You can remember it as DOPES, that is to diagnose the trouble. It is DOPES stands for displaced ET tube or ET cuff, which is not inflated or has a leak. O is for obstruction of the ET tube. P is for pneumothorax. E is for equipment malfunction, and S is for stacking or dyssynchrony of the patient. That is development of otospeep or breath stacking. So, and how you can fix it? You can fix it by DOTS. So what do? You disconnect the patient from the ventilator, give oxygen. You oxygenate the patient with a bag mask ventilation, and you feel for the resistance as you bag. Similarly, you can see the tube position. Did the ET tube migrate? Is it kinked, or is there a mucus plug? And suppose the patient has asynchrony, you can tweak the ventilator. That is, you can adjust the settings of the ventilator for the patient. And finally, the S is for sonogram or the ultrasound, which is commonly available in all hospitals now. So sonogram to look for pneumothorax, mainstem intubation, etc. So these are few of the troubleshooting and the fixes that are available. So DOPES is the one that can diagnose, and DOTS is the one for fixing the problem. So this is not the end, it's just the beginning of mechanical ventilation. There are a lot more things to do, but I think we will just go to a simulation so that we understand what has been talked till now. So just for the purpose, I will just go to a small simulator. We'll just take around 5 minutes. So we'll just am I audible?
Yeah,
Hello?
audible.
So this is just a simulator which you can download. All of you can, those who are interested or the people who are starting off ventilation, you can download the C6 Hamilton module from the internet, from the Hamilton website. It is freely available. So what you can see here is the patient's gender you have to enter into the ventilator. The height of the patient has to be entered, and whether the patient is active or passive. So we will do one passive one. So this is the ventilator, and you can see that this is a male patient. We can keep around 152 centimeters height. And so the ideal body weight or the predicted body weight as per the formula, the ventilator itself is giving you, so it is only 50 kilograms. This patient would be around 80 kilograms, but once you enter the height of the patient, you will get a predicted body weight. So you will be ventilating the patient only as per the predicted body weight. So now you just press the, you have to go to the, you can start ventilation. You can go to the mode. So we will do a controlled mechanical ventilation first. You just confirm the, so this is, you can see here, the mode is controlled mechanical ventilation, that is your volume control, correct? So what are the controls that you will set? So you can see here, FiO2 is set. I am just changing it. It is going to 60%. Okay. So you can set you have to set the FiO2. Similarly, you have to set the rate. So now I would like to set around 20. You can set whatever you want. And tidal volume, this patient has weight is 50. So ideally nowadays we set around 7 ml, 6 to 7 ml per kg. So we start around 6 to 8 ml per kg. So around 8 ml, the patient's 50. So we can keep around 350 to 400 ml of tidal volume. So this is a normal patient. If it was an ARDS patient, you would have kept only 6 ml per kg. And IE ratio you can keep around 1:2.5 or 1:3. We accept that. And we all know that if you keep pause time, you will get the compliance of the patient, right? So you will keep a pause time of around 10% of the total inspiratory time. So you will keep around 10%. Okay. And then you know your trigger. Triggers, you know what is you have to keep the trigger sensitivity. So either you can keep pressure triggering, or you can keep, so pressure triggering, sorry, if it is pressure triggering, you can keep -2 centimeters of water. Flow triggering, you can keep around 2 liters of 2 liters per minute of flow. If you keep very low, what will happen is the patient will, the ventilator will get even triggered with the presence of water vapor in the tubings. So you should keep at around 2.5 liters per minute, or a pressure trigger of around 2 centimeters. Now the flow pattern, if you look here, you can see that it is descending ramp pattern. But unfortunately, this simulator, you cannot change the flow pattern. If you change the flow pattern, it will switch off. So just see, look at the yellow color tracing that is there on the top. You can see that there is a you can see a peak inspiratory pressure as well as the plateau pressure, correct? Now suppose you remove the pause time, I make it 0, no pause. So there is a change in the waveform. You can see there is only peak inspiratory pressure. So it is very important when you have volume control ventilation, you give a 10% at least of inspiratory time hold. So you will get both the peak inspiratory pressure as well as the plateau pressure, right? So here now you can see another issue is you can see that the lung is there. You can see your EtCO2. Now, if you want, you can take a ABG, analyze the ABG. They are showing PaO2 of 420 and a PaCO2 of 38. So PaO2 is very high. So you can even come down on the oxygen levels, right? Now, suppose suddenly the rate has gone up. What happens? You can see that the minute ventilation alarm is ringing. So here we can silence the alarms, but then you have to do something. No, you cannot just silence and leave. So you should now reduce the expiratory minute volume is very high. So you can either reduce the respiratory rate or reduce the tidal volume, right? So that is what you can do. You can reduce the rate. So it will get back to normal slowly. Similarly, if the respiratory, if your tidal volume had gone up, again you would have had a high minute ventilation and patient would have had some problems. So this is regarding setting of a ventilator for controlled mandatory volume ventilation, right? Now, suppose you want to set a patient on spontaneous breathing. So spontaneous means pressure support alone. So you just confirm everything. So you can see that this patient was paralyzed and we have put them on pressure support. So the patient is not getting ventilated. So very important that we have backup setting. So that is called, if there is apnea, the patient will go into pressure controlled SIMV mode. So if you have, whenever you put a patient on pressure support, always keep a backup mode. So that is important. In pressure support, what are the things that you will set? So this has gone to this one. So we will just go back. In a pressure support mode, you will be setting only, you will be setting the pressure support level, the PEEP level, the oxygen, the flow trigger, and you will set the inspiratory rise time or the ramp time. So we usually set around 200, that is, you will get around 0.2 seconds. Okay. And if the patient has air hunger, you will shift to lesser ramp time in milliseconds. Okay. So this is regarding, so now since the patient was not breathing, it has gone to backup mode. Okay. So the other mode that I would like to tell is regarding pressure controlled ventilation. You just confirm and you confirm. Okay, so now you can see that the patient is on pressure controlled ventilation. There is you can see, just a minute. So this is the third one is the volume curve. You can see the volume one. So however, the main two graphics that we always look at is the flow scalar and the pressure scalar. Volume scalar doesn't give much information. So this is your pressure control ventilation. So the controls that you will keep are in pressure control is you will keep the level of pressure control. So now this patient is only 50 kilos, right? So you can see with 15 centimeters of water, the tidal volume generated is 545. That is too much. So we will just come down on the pressure control level. And you have to observe the change that is happening on the tidal volume. So an accepted tidal volume you should aim for, right? Then you should set the rate, you should set the PEEP level, the FiO2, the IE ratio, and ramp time in pressure control ventilation. The ramp time, or what is known as, there are a lot of terminologies being used, so we will call it the inspiratory rise time. That will be easier to remember. So now when you have reduced your pressure control level to 10 centimeters of water, you can see that the tidal volume has come down to 350 ml, which is reasonable for a 50 kilo patient. It is almost 7 ml per kg, right? So that is regarding pressure control. Then we have SIMV. So in SIMV mode, you will have to, as I have told you before, SIMV is not kept as a standalone mode. Always pressure support is added to SIMV. Here, what will you set? You will set the tidal volume. We will set tidal volume for around, he's only 50 kg patient. So we will set around 350 ml of tidal volume. You will set the FiO2. You will set the PEEP. You will set the respiratory rate. You will set the IE ratio. The IE ratio you can set. IE ratio. Similarly, you will set the pause time. It's a volume control mode of ventilation. So you will set the pause time so that we know what is the plateau pressure as well as the peak inspiratory pressure. And again, you will have to set here, because you have added pressure support, you will have to set the pressure support variables. That is, what is the pressure support level that you would like? What is the inspiratory rise time that you would like? And again, I had mentioned regarding the expiratory trigger sensitivity. If you reach 25% of towards the end, 25% of the end, you can, the ventilator in pressure support will, there will be the ventilator will cycle into expiration once the flow reaches, once only 25% of the flow is remaining. So that is expiratory trigger sensitivity. So what 25% is only remaining. So at that time there will be, so you can set it, if you want, you can set it at 50% or 30%. So usually ventilators set it at 25%. And again, you can give a backup mode for this. Usually you can give any backup mode you can put. Okay, so this is one more simulator where you just have to go to the Hamilton website, register your email ID, and you can freely download it and you can play with it and you can see what is happening to the various parameters. So this will be helpful for basically it will be helpful for all the students. So that is regarding the basics of ventilation. So since we have overshot time, I think we can
Sensor, please.
Yeah, since we have overshot time, I think we can discuss the remaining part a later time.
Sensor, please unmute.
Yes, yes, yes. Is it audible?
Yeah, now it's audible.
Yes, yes. I think, President Ganga, ഇതിന്റെ റിമൈനിങ് പാർട്ട് ഒരു സെഷനിലൂടെ നടത്തിയാൽ എന്താ പറയുന്നു?
Okay, okay. Papa Vijay, thank you very much for your excellent talk.
Thank
And
you.
thanks a lot. Hope everybody has understood the basics of the fundamentals of mechanical ventilation, and the rest will be taken